Here's part 3 of our NMR discussions. This is the last part, and we're going to take a look at some more advanced topics without getting into gory details. But let's talk about some coupling constants. And I'm going to say that this is one more piece of information that you can get from NMR, but it's really, truth be told, it's related highly to the splitting issue. We just managed to talk about the N+1 rule when it comes to splitting, and that was the last little piece of information. So coupling constants, we'll talk about this, what they are, how they pertain to the N+1 rule. The problem, too, is that not every single signal, of course, there's always problems. The problem is that not every single signal obeys the N+1 rule. So whenever, and I mean whenever you see a signal that doesn't quite look like a traditional N+1 pattern, like a quartet triplet, something's kind of amiss. In other words, the intensities of the quartet or the triplet don't follow Pascal's triangle for the intensities. It's probably a complex splitting pattern, and that's why we need to talk about these tree splitting diagrams. We're not going to really spend terribly large amounts of time on this, but I think it's interesting. You may get this. I think it's pretty easy to understand. I'm going to do the best I can to try to explain it to you. So we're going to talk about complex splitting is what we're going to talk about. So complex splitting, these splitting patterns do not obey the N+1 rule. Okay, so let's take a look. Now here's what I'm calling a simple example. You may not find this so simple. Now when you first look at this molecule, we're looking at, this is propanal, it's called. It's an aldehyde, and it's got methylene group here. These values that you see here, these are called coupling constant values. These are normally things I look up in a table. And what I found in the table is that the coupling between this hydrogen and this hydrogen, the coupling constant, is 7 hertz. Okay, so that's a value that you typically see associated with coupling constants. The thing is that this coupling constant between this hydrogen, or this hydrogen, doesn't matter, and this hydrogen is 3 hertz, so very distinct values. And when it comes time to look at the splitting pattern for these central 2 hydrogens, we're going to see that this is going to give rise to a complex pattern. And the reason for that is because the coupling constant between these two and then these other 2 on the left side, it's different, and you're going to get a complex pattern every time that is true. Okay. Now, the other signals, the methyl group and this aldehyde hydrogen, let's look at those first because those are actually more predictable. Those work with the N+1 rule. So let's look at the methyl group, and really to look at the methyl group, we can look at any 3 of the hydrogens. So let's just pick this one arbitrarily. And the coupling between this hydrogen and this hydrogen is 7 hertz, but likewise the coupling between this hydrogen and this hydrogen is also 7 hertz. And the way you set up a tree diagram for this, and this is the signal down here, by the way, I'm going to circle this. That's the methyl group. The way you do this is you set up a tree diagram. Here's the start of it. So it starts at the top. And the first thing that you do is we're looking at the coupling between these 2 hydrogens right here. Okay. Now, we talked about this in part 2. This hydrogen at any given time can be spin down or it can be spin up. And really that represents a 7 hertz difference in the shift value. Okay, so that's what that represents, whether the neighboring proton is spin down or spin up, 7 hertz. And that's why we've drawn this splitting diagram such that there's a gap of 7 hertz. And by the way, I drew these in Illustrator, so these are to scale, and that's really important when it comes time to make tree diagrams. You'll either have to do this on graph paper or in a program like Adobe Illustrator. Okay, so that's just considering the first hydrogen. Now what about the coupling to the other hydrogen? So remember, we're still talking about this signal right here. This is still the one we're talking about, but we have to consider the other coupling, and that's when we go to this second tier. So this is the second hydrogen that we're coupling to. But once again, we get to here, and the gap is still 7 hertz. Okay, because the coupling constant is the same, and likewise over here, it's still 7 hertz. And actually, you don't even have to do a tree diagram because what you get is just a traditional triplet is what you get. So the intensity is the lowest here equal low, and then the middle one's the most intense. And that's exactly what we see here. And the N+1 rule applies to this because the coupling constants are all the same. So N+1 definitely applies for this situation. It's not necessary to do this tree diagram for this. Okay, N+1. Likewise for this aldehyde hydrogen that's way down here, this one also obeys the N+1 rule because the coupling of this hydrogen, let's erase all this other business here. So the aldehyde hydrogen, the way it couples to either one of these two hydrogens on the left is the same coupling constant. So once again, the pattern is going to be a traditional n+1 pattern. So this is a triplet. That's exactly what we predict. There's two neighbors, triplet pattern. But if you look even more closely, though, the gap between these three of the multiplet is a little bit bigger than the gap between the three little mini peaks in this triplet, and that's due to the coupling constant. The coupling constant, quite frankly, is bigger here, and it's smaller here. They're both triplets. They both obey the n+1, but the coupling constants are different. Now we get to the beast. Okay, the middle splitting. And that's going to be the signal for these two hydrogens right here. So that's the signal. Now we only have to really look at one of these two because they're both identical. They're equivalent. And you can see right away that the signal does not obey a traditional n+1 rule. So that's right away you see something complex. We call this a complex signal right here. It does not obey the n+1. So the analysis actually is quite complex sometimes. And what you need to do is, again, I'm just going to circle one of these hydrogens because doing this tree diagram for one hydrogen of these two is doing it the same for the other. So on the one hand, what you got to do is we're going to tackle this one. And the first thing that we're going to do is just look at its coupling to that hydrogen right there. And that gap is, once again, 7 hertz. Okay, there's no change there. And then we look at the coupling to this hydrogen, 7 hertz. So both these little gaps right here are 7 hertz. Then we look at the coupling to this hydrogen. The gaps are 7 hertz. And so far, so good. That would be a normal quartet if we could stop there, that is. But unfortunately, the coupling to this hydrogen, on the other hand, the aldehyde hydrogen, is different. And that coupling constant is 3 hertz. So these gaps right here, all of them are 3 hertz. Okay, so that's why these are the tinier gaps, and that's why we don't get a traditional n+1 pattern, because now this pattern right here is exactly what you see at the end of the tree diagram with the spacing and the bigger gaps here and the smaller gaps here. So that's how we do or predict this complex pattern. It does require a knowledge of the coupling constants. When I advance this slide here, you're going to see a table that's in your textbook with some pretty quick coupling constants that you can look up. But with very complex molecules, and it gets really hard to predict with the coupling constant. Right now, I'm running an experiment with Gaussian, which is a molecular modeling program, and I'm finally trying to figure out how to computationally measure coupling constants. But it takes a lot of computing power, and I'm not sure I'm going to finish in time before this lecture is done. Okay, so let's move on to another example. Now here's one of my favorite molecules. This is called cinnamaldehyde. I like this molecule because it smells really nice. It smells like Christmas time. And let's do this. Let's think about this for a second. So the structure is essentially this one, or the structure is this one. So I'm proposing two possible structures. We've got everything figured out except for the nature of the double bond. We don't know whether it's a E or Z double bond. So here's where coupling constants can really come in handy, because if it's truly this, which is a cis double bond, we're going to predict, let's see, how did I do this? We're going to predict this tree diagram where for the cis hydrogens, we've got a coupling of 10 hertz, and then the coupling between the hydrogen and the aldehyde is, well, let's see, where am I? I got to find these. Okay, so here's the cis coupling, it's 10 hertz, and then the other coupling that's possibly going on here, oh, it's not on this chart. That's why I can't find it. We just saw it a second ago. I think it was... I cannot remember now how I got that value, but let's just assume that it's approximately the same as, let's just do this. We're just going to call this 10 hertz. I'm trying to think of where I got the value for the coupling for the aldehyde hydrogen. Oh, I know what it was. Okay, so I just remembered. It's the allylic. I got it from here. So it's 6 hertz. Okay, so it's a hydrogen that's 1 carbon removed from the allylic position. So that would be this one. Although that's just a guess that it's 6 hertz, but it works. Okay, so the gap here is 6 hertz, and of course 6 hertz here. Okay, so that's if the double bond is a cis double bond. We would predict this tree pattern versus the trans double bond, where the trans hydrogens are coupled a much bigger coupling constant of 15 hertz. That gap is already wider than the cis version, so 15 hertz. But nonetheless, this gap, I just assumed that is 6 hertz still, because they're pretty much the same distance from one another versus the cis version. So, okay, but anyways, we've completed the tree diagram, and notice that the spacing from here to here and here to here, it's almost the same, not quite perfectly the same, but pretty much the same, versus the spacing over on this left example here, and then the gap is tinier here, and then a bigger gap here. So then when we finally look at the actual signal in an actual NMR spectrum for I just came with the answer, trans-cinnamaldehyde, we see that this pattern, this is the zoomed in one, looks a lot more like this one, where the gaps are pretty much the same. And so you see that with the gaps here, they're pretty much the same, versus big gap, small gap, big gap. That's not what we have. And so the true structure of this is not that one. It's actually this one. We use coupling constants to prove that. Okay. Coupling constants are often really hard to measure on your NMR spectrum because, you know, if you got a lot of overlap or the resolution's really poor, it's sometimes really challenging. And when I was making the notes for this lecture, it was really frustrating to me because I wanted to look at a bunch of molecules that have complex patterns, but you just simply could not see the gap or measure the gap. The way you do this on paper, though, is if you print out your NMR spectrum, which I frequently do, I print it out, and then I measure literally with a ruler the gap in millimeters between these things, and then I try to figure out how many millimeters between a 1 ppm shift, so 6 and 5, and then I do a bunch of calculations, and I can actually figure out the coupling constant once I've factored in, I've converted to hertz and all this kind of stuff. So, but that's how you traditionally do it. You print it out, you measure this gap, do a couple of calculations, and you measure it. Okay, and that proves, in this situation, it proves trans-cinnamaldehyde versus the cis. Okay, so let's. I think I have one more example, just one more, I promise. I mean, we're really beating this to death, but I kind of like the discussion, although I'm not sure that I've ever asked this on a test except for an extra credit question one time. But here's a molecule. I wanted to put this one up here because this is something we're going to synthesize this semester via Diels-Alder reaction. And this molecule looks quite complex. It's a bicyclic compound. But the truth is it doesn't have too many hydrogens. There's a couple more hydrogens here at the bridgehead position. And then there's a hydrogen here and a hydrogen here. And, of course, the double bond has hydrogens. Now, when we do the NMR, we don't get quite the resolution of this, so I dug the spectrum up from aldridge.com and gives much clearer resolution. In fact, furthermore, on our NMR spectrum, you don't get any resolution there, and you don't get any resolution here. I'm only going to really focus on a couple of things in this spectrum. First of all, let's just get the easy stuff out of the way. So these two hydrogens are vinylic hydrogens. They're definitely going to be this signal, and I'm not going to say anything more about that. These hydrogens this is another bridgehead position. They're going to be lumped in here with these other bridgehead hydrogens, which are lumped right next door. Okay, so all these are kind of mashed together right here. The interesting signal are these two right here. This is what I'm really interested in. And these relate to these two hydrogens at the very tippy top of the hat of this bicyclic compound. And when you look at these two hydrogens closely and you ask the question, are they homotopic, enantiotopic, or diastereotopic? They are, as it turns out, diastereotopic. And usually when you've got hydrogens that are permanently fixed in different local magnetic environments, which these are, they're diastereotopic, you can get complex patterns. In fact, you're always going to see complex patterns when that's so. Because the coupling constants, by the time we're ready to sort of measure those, and I'll just tell you right now, it's really hard to get coupling constants for this molecule because you just can't measure it. This is just so tiny right here. But I did the best I could. I measured them as best as I could. What I had to consider is coupling. When you have diastereotopic hydrogens, which you do at the very tippy top here, they couple to each other, as it turns out, because they're in local magnetic environments. So only diastereotopic hydrogens have coupling constants between them, or at least ones you have to consider, and we do have to consider it. Okay, so these are coupled together, and in both these tree diagrams, that is the biggest gap right there, surprisingly enough, is the coupling of the two hydrogens that are diastereotopic. Okay, so that's the biggest gap in both of them. So this gap right here and this gap right here are the same between them. Okay, there's no difference between them. Now where it gets different is the way this one couples to the bridgehead hydrogen versus the way this one couples to the bridgehead hydrogen, and likewise they couple the other direction too. Notice that the gaps are much smaller for this one versus this one. And when I looked really, really closely at this first peak right here, really closely, it looks like this pattern right here. And when you look at this one really closely, it looks like this pattern right here. And I don't remember which one's which. I'm sorry, because it's really hard to figure out here. But that's what you see when you really zoom in into this. And it's just that they have slightly different tree diagrams because they're, like I said, they're permanently fixed in slightly different local magnetic environments. So that's how you do the coupling constants, though, is you have to consider to themselves, to each bridgehead, and you get a complex pattern as a result. Now, when we finally do the synthesis, we're not going to see much of anything. So if you're interested, you can dig up the spectrum from aldrich.com. It's there. I forgot how to name this. I ended up drawing it in Aldrich. Aldrich is really nice. It allows you to draw the structure, and then it'll do a search on the structure. I drew it in. I found it, and there's an NMR spectrum for it. Now, here's the coupling constants. These are in your textbook. I'm not going to really use these in any way. I'm just going to tell you that this is how I got the patterns. I think that's all I want to say about coupling constants. If you really are curious about this, you can talk to me in class tomorrow. We can kind of look at some other stuff, and maybe my modeling study will be finished. And I can actually, I'm modeling this one on the computer, and I really want to home in on the exact coupling constants for all these hydrogens. So I'll let you know if that happens. Let's move on to carbon NMR. So we haven't talked about carbon NMR yet, but there's not a whole lot to say because we really, in terms of compared to hydrogen NMR, we get a little bit less information. So all the principles are still the same, but less information. Here at Shasta College, before I got here, slightly before I got here, about 10 years ago, we had no capability to do carbon NMR. It's only because we had a FT, so Fourier transform upgrade to our magnet, that we can do this. Now, carbon NMR spectrum is more difficult to obtain for several reasons, and right now I'm going to get into those reasons. Here's the limitations of carbon NMR. See, these are some hurdles that we sometimes have to get over. It's the same theory as HNMR, but carbon generally is run broadband decoupled. That's a fancy term that means that the splitting is specifically turned off in a carbon spectrum, so you don't see any of these multiplet patterns. And there's some tricks about how you do that. I'll let you read about it in the textbook. But broadband decoupled, that's what that means, no splitting. Integration is not usually performed on CNMR, unfortunately, because the area underneath the curve is not proportional to the number of carbons that are represented, and that relates to carbon-13 as the active nucleus. The last little hurdle, which is sometimes the biggest hurdle, requires very concentrated or more ideally pure liquid samples, especially for our NMR, because we really can't do carbon NMR unless things are pure or highly concentrated. Even the highly concentrated samples that I've run over the past, I frequently have to run them overnight just to get enough signal to work with. And the reason for that is because you pick up any sample of carbon-containing molecules, and only 1% of that sample is going to be due to carbon-13, so it's very low abundance. Carbon-12 is the main one. Unfortunately, carbon-12 is not active. Carbon-13 is. Okay, so that's some limitations, although for the most part, if we have concentrated samples, we can do it. The advantages, for sure, are better resolution. So already you've got a chance to collect some CNMR spectra, and you get much better resolution compared to HNMR, even on our NMR magnet, especially on our NMR magnet. Our hydrogen NMR is pretty low resolution, but carbon is very sharp. It's easy to find the peaks. So that means that it's easy to detect magnetically non-equivalent carbons really easily in the NMR spectrum. It's also obviously great for compounds that have too many or too few hydrogens, of course. A lot of these natural products that people discover in nature, they have so many hydrogen that it just becomes a mess on the HNMR spectrum. It's hard to interpret it. We talked about ozonolysis last semester as one way to break down the molecule into smaller pieces, but nonetheless, it's kind of difficult. Now, depth is something we'll talk about eventually, but depth is distortionless enhancement by polarization transfer. That's a fancy set of words, but really depth, it's a different type of experiment, but nonetheless, it's still carbon-13, and it's really powerful, and we did this in our laboratory. I'll talk about how that works. Now, here's a typical CNMR spectrum on the right side, and its corresponding hydrogen NMR is on the left side, so this molecule is called carvone. And right here in the carbon spectrum, you can clearly see the carbon signals. There's 1, 2, 3, 4, 5. This one is 6, 7. I know it's 2 signals because the computer marked it as such. 8, 9. and 10. I can tell you already that that's the right number of carbons. This compound is called a terpene. Terpenes are natural products. They always come in, they're really cool. They're my favorite type of classic compound. They come in multiples of 5, so this one's 10 carbons, and that makes sense. By the way, this is TMS, of course, so this one doesn't count. Anyways, you can clearly see these carbon signals. There's no question of it. And similar to NMR, the shift, the chemical shift is very important. I can tell you right now that this is the carbonyl carbon, so this one right here corresponds to this one. Okay. The other ones are going to be hard to figure out, but I'll show you some depth experiments that will make it a little bit easier to do this. Now compare that to the hydrogen NMR. The hydrogen NMR is a complete mess. You expect a little bit of splitting patterns, clean splitting patterns, forget it. It doesn't happen. This thing's a mess. Everything's a mishmash of stuff. The integrations are accurate, so you can see that this is 1, 3, 8, and then 14 total hydrogens. That's fine, but you just don't get a whole lot of information. In fact, this one represents several different types of hydrogens right there that are all just mashed together. But the carbon, very clean, very easy to interpret. Now, here's a shift table for carbon NMR that you're always going to have. It's in your spectroscopy unknown determination guide. There's not a whole lot to say. Carbonyls are the thing that appear from 160 to 220, so those are very distinctive. Aromatic stuff, double bonds, nitriles, those are all kind of in the middle. Triple bonds, just like in NMR, a little bit further upfield. CO, CN, halogen, methine, methylene, methyl, so these approach 0. So just like in hydrogen, pretty much similar story. The last carbon experiment that we can do here at Shasta College is called a depth experiment, and this is really powerful in combination with carbon-13 because for each carbon signal that we detect, we can figure out how many hydrogens are attached. It stands for distortionless enhancement by polarization transfer. There's a mouthful. That's why we use the acronym for short, DEPT. There's 3 separate depth experiments. The lowest one is called a depth 45, depth 90, depth 135. The numbers themselves have to do with the angle of pulses that the carbon experiments do. I just don't want to get into the gory details, but that's some differences in the way the sample is handled. But anyways, when you look at depth experiments, we're not seeing the original carbon-13 experiment, which would normally show all the carbon peaks. So in this spectrum, all the chemical shifts are going to be the same, but some peaks are noticeably absent. I think we had a carbonyl somewhere down in this region, and it's completely absent from this spectrum, but that's actually something in and of itself. So if you come down to this table, which I always get made fun of in this table, it's kind of not so clear the way this works. As soon as I get the time, I'll remake this table. But so absent, absent, absent in all 3 of the depth experiments, what that means is that that's a carbon with no hydrogens attached, and that makes total sense because the carbonyl in carvone has no hydrogens attached, so that makes perfect sense. On the other hand, this signal right here is present, present, present. It's up in every case. This is a carbon that has 1 hydrogen attached. It could be, I'm probably going to go on a limb here and say it's this one right here. I'm pretty sure it is because, it could be this one too. I'm not quite sure which one it is, but it's a carbon with 1 hydrogen attached. Now this carbon is down, up. So what that means is that, let's see, if I come to my table, the only one that's down in the upper one is this, which is a carbon with 2 hydrogens attached. Okay, so when we come to these peaks, remember these peaks are really close together, so don't be fooled. So there's a down one, and then way down here is an up one. And so what that signifies is that this down one right here is the same one as that one. It's not the same carbon, but the same type of situation. So carbon with 2 hydrogens attached, and then all the other bonds are to carbon. Right next to it is an up peak, up, and then it's up here. So that's something where all 3 of them are up. That's going to be a CH. All right, so that's the other CH right there. Truth be told, I think this CH is the one that's at this position, and then the double bond CH is the earlier one. Is this one right here? Okay, so here we have one that's down, up. That's going to be, once again, that's going to be a CH2. I'm just going to write a CH2. We've got up, absent, up. That's going to be a CH3, and the last one is a CH3 as well. So that's the usefulness of this. We can see carbons and how many hydrogens are attached to them. So really powerful. In fact, it almost allows us to skip the hydrogen NMR entirely if we can do this experiment because it's really powerful. And just so 3 carbons are going to be missing from this depth experiment. I've already pointed out that the carbonyl carbon's missing, this one's missing, and then this one's missing, of course, too, because these are all carbons that have no hydrogens attached, so they're completely absent from this experiment. So whenever we can, we run a depth experiment. We did this with the unknowns, really powerful to use this. Now, finally, the last couple of examples and discussion is unknown structure to determination. So in the laboratory, you're doing this right now, and in class pretty soon here, I'm going to pass out some unknown determination sample problems. There's about 6 of them that I traditionally pass out. But just to kind of give you the gist of this, most pharmaceuticals that are here with us today are still, for the most part, a good guess would be that they're from nature. Okay, so when chemists go out to nature, these organic chemists, they go on these fancy dive trips. They go down to South America and they find these plants, and they bring the plants back to the laboratory. They extract them with solvents, and they just kind of see what kind of chemicals these plants are producing. And I'm not going to say that a lot of the time they find useful stuff, but they find sometimes brand new molecules that the plant is using for one reason or another, but they sometimes turn out to be good pharmaceuticals. And then even if they're not directly a good pharmaceutical, at least they're a good start point where you can chemically modify it. But one of the big jobs is once you get that new molecule, the first job is to isolate it, and that is sometimes months of extractions and just experimental stuff. And then even when you get the compound in pure form, there's often just tiny amounts of it. We're talking about micrograms sometimes, milligrams, if not smaller, but you got to figure out the structure at that point. And so with tiny amounts of sample, you got to be really careful about not wasting any of it. So you try to figure out the structure, a lot of spectroscopy at that point. Sometimes they'll do ozonolysis like we talked about last semester to break down the molecule. If it's really large molecule, they got to break it down into smaller pieces. For us, I passed out an unknown structure to determination guide. You're going to get a chance to bring that into the lecture when we take tests, and bring that with you tomorrow in class because you're going to need that. And let's take a look at how this works. So I've got 2 sample problems for you. This is the first sample problem, and we're going to figure out the structure. That's the whole goal, using spectroscopy. What's the structure of this compound? I tried to white out all the structure names. I think I took care of everything. So the first step is always to determine the form and mass of the compound. So if it's not already stated, here's the mass spectrum. And the first thing that catches my attention right away is that there's a bromine atom in this. This is the characteristic pattern for bromine in the mass spectrum. And I'm just going to go ahead and try to figure out what that form of mass is. It's 2, 4, 6, 8. And that's for, so that's 198 for bromine 79 specifically. Or I could bump this form of mass up to 200 and use the other isotope of bromine. But anyways, bromine 79, 198. And then what else should we be looking at? I'm going to look at the IR spectrum really quickly. I don't see anything that jumps out at me. Oh, I take that back. Actually, here's something that jumps out. This is a conjugated carbonyl, so this is a C double bond oxygen that I see right away. It's not very strong, but it's there. It's pretty close to 1700, and it's conjugated, so that shifts the value a little bit further towards 0 at 1680, but that's a carbonyl peak. Down here, this may look like an alcohol, but it's nothing. And I don't see much of anything in this region right here. Not a whole lot going on besides the carbonyl. So we also have at least one oxygen, so I'm going to go ahead and jot this down. So bromine 79, definitely have one of those. As far as I know, there's only one oxygen. Most of these compounds that I pick only have one functional group, maybe 2 at the most. But anyways, now when I look at the NMR, I can quickly figure out the hydrogens. So 4 plus 3 is 7 hydrogens, so I'm pretty confident of that. The carbon is a little bit trickier, so when I look at this carbon spectrum, 1, 2, 3, 4, 5, 6, there's 6 carbons that I see, absolutely, but there might be some hidden ones. By the way, this set of 3 peaks right here is not part of your molecule. If you see this, if you see it, it's due to CDCl3. That's actually a strange thing that happens with deuterochloroform. So you just totally ignore this. It's not part of your compound. Whenever you see that set of 3 peaks there, ignore it. It's deuterochloroform. So 6 carbons that I can safely see. Now here's the real trick, actually. I know from experience that these are aromatic carbons, and all the unknowns that I've ever given have benzene if they have an aromatic part to them. And so right away, just based on my own experience, I guess you would say, I only see 4 here, but we know that benzene has 6. So the true count of carbons is 8 carbons and not 6. So I'm going to go ahead and scratch that out. So it's 1, 2, 3, 4, 5, 6, 7, and then 8 is the total number, so 8 carbons. I'm pretty confident now that the chemical formula is C8H7 and then BrO. You can double check that. I don't have the, well, I do have a calculator. I better check this. Okay, I was about to say, I can't do this, but I can. All right, so 8 times 12.01 plus 2, excuse me, not plus 2, plus 7 for the hydrogens, plus bromine 79, plus 16. So that comes to 188, which is perfect. So I'm confident that this is the chemical formula right here, C8H7BrO. And that is the first step in terms of figuring out the structure. So we're going to have to remember this structural form, this chemical formula. And so I'm going to move on to the next slide here. Okay, so I'm going to go ahead and clear the slate. I got to remember what this chemical formula is, C8H7BrO. C8H7. I keep doing that. I want to make that a 2 for some reason. Okay, H7BrO. Okay, so the second step in the method, if you're looking at the structure determination guide, is to determine the units of unsaturation. So with this compound, remember halogens count as hydrogens. So 8 times 2 is 16 plus 2 is 18. Now 18 minus effectively 8 is 10. Divided by 2 is 5 units of unsaturation. I'll just tell you, so here's a little bit of intuition for you. With 5 units of unsaturation and relatively few carbons at 8, that just smells of benzene right away. Benzene is something that has 4 units of unsaturation, and then we already know the carbonyl has 1 unit of unsaturation, so that makes perfect sense that there's a benzene ring and there's a carbonyl. A lot of units of unsaturation, very few carbons. Okay, so that's the hint. Now, so I'm pretty confident that we have a benzene ring. I'm going to go ahead and show that right here. So that already takes care of most of the carbons right away. That's 6 carbons. Now, what's the substitution on this benzene? Does it just have one thing attached, or 2, or 3, or 4? A couple things are helpful. I think the most helpful is just simply put the integration. So it says 4 there, which means that there's only 4 hydrogens left. Okay, so we don't know at this point, though, how they're orientated. So let's just go ahead and say that, there's one group for sure that's maybe there, but we don't know if it's ortho or meta, para. We'll try to figure that out as we go. Okay, so what else is attached to this? We already know that there's a carbonyl. We only have to account for 2 more carbons. We've already got 6 carbons accounted for. So I suppose on the one hand, we can guess an aldehyde and just put the carbon somewhere else, the other carbon somewhere else, but we don't see any indication of an aldehyde here, so I'm fairly confident that there's no aldehyde, and that's probably the wrong thing to do. So I'm going to go ahead and erase this. And I think instead what I want to do is I want to put CH, well, let's see, is it CH2 or CH3? When we come down to this depth experiment, here's the carbon signal for the CH3. It's the most upfield. So CH3, I see CH3 there. The integration proves that, but also furthermore, the depth says that it's truly a CH3. And so I think I'm pretty confident that that's a CH3 group. Furthermore, the chemical shift for hydrogens adjacent to a carbonyl is just about right at this chemical shift right here. Okay, so I think that's how that structure goes. We've got the carbonyl taken care of. It's conjugated. Here's the methyl group. Now, what about the bromine? So the hardest part, and we've almost got the structure already, is to know whether it's ortho, meta, and para. You don't have this, but from intuition, I see that this pattern looks a lot like looks a lot like para substitution. So I'm going to go ahead and say that I think that's a bromine. And let's just see if that's consistent with the carbon signals. So for carbon signals, I would see 1, 2, 3, 4 different types of carbon, so that's definitely consistent, versus the meta substituted. Let's just kind of draw this for a second, see what happens. So meta would be Br here, and then the other thing here. So that would be how many total signals? I think that's going to give us 6 signals. So 1, 2, 3, 4, 5, 6. Yeah, so this can't be it. What about the ortho? That was the meta. Here's the ortho. I'm getting worse and worse. My pen is getting trapped underneath my microphone here. Bromine. Other group. How many total signals? Once again, I think I see 6 signals. So I think without a doubt, The fact that we only see 4 signals here really says that there's para substitution, and I think that's it for the compound. You can check for yourself, but there's 8 carbons, there's the proper number of hydrogens, there's a bromine and a ketone, and this is a done structure. Sometimes we run into these types of problems where there's more than one right answer, so if you don't quite come up with the same answer that I do, a lot of the time I'm going to give you full credit anyways because your structure is consistent with the data. In fact, that's happened quite a few times on tests. So don't freak out if you don't get exactly what I get. As long as it fits the data, you get full credit. All right, so that's it for that sample problem. I have one more sample problem for you. Let me show you that. All right, I'm re-recording this problem for the 3rd time because I finally discovered what the problem was on this problem. But this is another sample problem where we're going to get a chance to figure out the structure of this unknown determination. We're going to start by determining the formula mass of the compound. The problem that I ran into is that the parent peak is not observed. It's actually 88 atomic mass units. I can tell you that now, and that sometimes happens with mass spectrometry. I'm always going to tell you when that happens, so don't worry about it too much. That's my bad. So 88 atomic mass units, at least I think that's what it is. It's definitely not this, though. That's where I was going wrong. Okay, with that in mind, what we clearly see is an alcohol group, and so there's 1 oxygen, or maybe more, but for now 1 oxygen. There's clearly at least, and I say at least 4 carbons, so 4 carbons. And then hydrogens, there should be 12 hydrogens. And so what we're going to do at this point is check to see if that adds up to 88. And let's go ahead and punch that into the calculator. So 12 plus 4 times 12 plus 16. Okay, right now we have 76, which is just 12 short of 88. And so, of course, since we're 12 atomic mass units short, that must mean that we have 5 carbons and not 4. So the true structure, true chemical form is C5H12O, and it must mean that there's some symmetry in the molecules such that there's a hidden carbon that's kind of masked by one of these carbon signals right here. So C5H12O. So now we can move on to the other parts and try to figure out this structure. So let's do that. Okay, so I'm going to rewrite this as quickly as possible. C5H12O before I forget it. Now let's start with the alcohol. So there's definitely an alcohol group in this. No question about that. There's at least 4 carbons. Well, we already know that there's 5 carbons. And then furthermore, there's all these hydrogens right here. I can also tell you, too, I'm going to have to help you with this. This happens to be a quartet. I'm just going to mark this as a Q. This happens to be a singlet. And then this one happens to be a triplet. Okay, it's really hard to see this, but I can tell you that that's what's going on here. Now, still, we only know for sure that there's an alcohol group, and that corresponds to this in the hydrogen spectrum. Of course, it's in the infrared spectrum too. But there's only so many ways we can put together a 5-carbon molecule with an OH on it. So let's just try a bunch of different ways. I suppose the first thing that I'm going to try is just join the carbons in a row. And really what you need to do, and a lot of the time you need to do this, is just brute force, where you try a bunch of structures, see if they're consistent with the data. And I can tell you that this is probably not consistent with the data because with a singlet, we're talking about a hydrogen with no neighbors, and it's not the hydroxyl. So this one even has neighbors. So this can't possibly be the structure. Keeping these things in a row, let's just try putting the OH at the end, but I think we're going to have the same problem where there's no way to have a singlet in a structure like this. So we're forced to, well, maybe one more possibility here. We'll just put it in the middle. But once again, can't happen because there's no singlet possible in that structure. So we've exhausted all the possibilities where we have all the carbons in a straight chain, OH at the end or in the middle, whatever. None of those are going to work for us. In terms of the hydrogen spectrum, none of those are going to fly. All right, so let's try some branching in the compound. So let's go ahead and just take one of those end carbons and just simply move it to maybe this position right here. That's all we can do, and try some alcohol. So if we put an OH here, try some alcohol. If we put an OH here, do we have a singlet possible? And the answer is no. There's 2 hydrogens here. I don't see any singlets possible, so that can't be it. Let's try putting the alcohol maybe here and see what happens. And actually, this might look pretty good because these are CH3s. And all 6 of these hydrogens are magnetically equivalent. They don't have any neighbors, so that would be a singlet. What else do we have? We have a CH2, which has, let's see, this CH2 has 3 neighbors. That'd be a quartet, so that's consistent. And then these CH3 have 2 neighbors. That'd be a triplet. So far so good, actually, in this structure, and the OH is still there. Now, let's confirm that there's 4 carbon signals, but what type of carbon are they? How many hydrogens are attached? This is going to be a CH2 right here. This one is going to be a CH3, and then this one's going to be a CH3. And we normally don't integrate carbon signals, but nonetheless, a lot of the time the signal's bigger for 2 CH3s versus just 1, and that seems pretty consistent with that, so everything is kind of hunky-dory. Meanwhile, we're missing, oops, we're not missing that one. We're missing this one right here, which is not present anywhere down here. So that must mean that it corresponds to this carbon with no hydrogens attached, so that seems pretty consistent. What else can we do here to prove this? I think that's about it, actually. I think this is the structure that we come up with. I forgot to mention in the first sample problem that I normally require you to do what's known as peak assignments too. So we're pretty confident that this is the structure. I'm going to go ahead and clean the whole slate. And the last thing that I want you to do on laboratory experiments, but also then the exam, is to do what's known as peak assignments. So what you're going to do is you're going to draw the structure again on each spectrum. And I want you to draw an arrow from each type of hydrogen to which signal it represents in the NMR spectrum, but also the carbon spectrum. So for this OH, that's that signal. Now both this one and let me use a different, I'll tell you what, let me use a different colored pen to kind of indicate these other ones. So the blue ones are both the same chemical signal, and these would normally point to here. The green ones, which should be a quartet, is going to be here. And then finally the red ones, which are at the end, are going to be there. Okay, so that's called peak assignments. So for every signal in the NMR spectrum, you're going to indicate where in the molecules those are. Same goes for the other spectrum, which is the carbon spectrum. Let's draw this molecule here, like so. And so for each type of carbon, you're going to do the same thing. Let's start with the carbon here, which is that signal. These methyl groups right here are, I believe, the bigger of the 2 peaks. So here, yes, even though we don't integrate, still you can probably assume that the bigger peak is 2 carbons versus 1. And that brings us to the next carbon, which is this one. And that one, according to our results, is going to be this one right here. And then let's see, finally, we've got this one right here. Okay, so sometimes they make you do this on the IR spectrum, sometimes not. It's a little bit trickier here because it's going to be hard for you to know what I want and what I don't want. But of course, the OH bond is the most significant piece of this infrared spectrum, and that's going to correspond to that. And that's pretty much all I would want you to mark on the peak assignments. But this is something we always do in spectra. So whether it's the laboratory or the lecture, I always want you to do these peak assignments, and you'll see that on the exam, the practice exam. But that's it for this part 3. This one a little bit longer than I thought I would, but we're going to get more practice on how to identify compounds. I'm going to pass out about 6 sample spectra and have you take a look.